keyboard on this computer. Okay, so 4.7, we're going to learn what's called the normal distribution. And what this is a particular shape that a data set takes. So it's when a data set has a set of characteristics about it. We're going to learn about that, and it's related. It's a special characteristic of a data set that relates a mean and standard deviation. It's quite useful. We're going to understand that there's a connection between area under a normal curve. So we're going to figure out what all that means. And then that connection and the percent and probability. So we're connecting that probability back to section 4.1 that we talked about. And then we're going to get a basic understanding of the empirical rule, which is what you're using in the project. And we're going to learn what a z-score is, all this mess. So let's talk about this normal distribution. Turns out there's lots of things where that are called normally distributed. You know what? I didn't ask if anyone had any questions about anything. Does anyone have any questions about anything before I just like dive in and go nuts about this?
I was wondering how you make a stem and leaf plot with a certain number of classes.
Great question. That's I'm laughing because that was a terrible question in the worksheet that you should just not do. Are you talking about question number 1 from 4 or 5?
Yes.
Don't do that. That's how you do it.
Okay, sounds good.
So really, like, there isn't stem and leaf plots. The way the stems work is you just they're picked based on the numbers. So you can't have like a specific amount of classes. And then when you look at this data set, a stem and leaf plot is just awful for it. Like the stems would be 9, 10, 11, 12. And then the leaves would be this 3, 6, 9, 4, 8, 5. And then the 10 would be 1, 4, 9. And 11 would be 0, 4, 9. But it just like, it doesn't give us a good look at the data. So this was a really bad question. Just throw it away. Don't do it. So thank you for asking that.
Okay, and then the histogram we can do?
This one's okay. What I would do for this is use 5 classes. So keep it really small. And it will have a similar setup as the 5 class, the one we did in class up here. I think this one has a few more data values than that one. So it has a higher maximum. So it just has like 2 more values in it. So it will look, in terms of the frequency distribution, it will look very similar to the one you did here.
Okay,
but then
thanks.
You're welcome. You got it. Good question. Okay. Any other questions y'all got? All right. So what happens with the normal distribution, or when data is normally distributed, we have the majority of the numbers, or the majority of the data values fall in the center of the data set, meaning the mean. So a normal distribution has a center that's equal to the mean. And then there's equal amounts of data going in either directions. So let's kind of pull that out. It turns out there's lots of things in the natural world that end up being normally distributed. Our author took out, like, collected these links of maple, what are these, maple pods or whatever? And this roughly looks like a normal distribution. I mean, I kind of question the measuring on these. I mean, that looks like it's 58 to 59. The idea here is we've got most of the pods are right here in the middle, and then there's equally amounts on either side, roughly. And that's what we mean. That's kind of what it looks like for a normal distribution. It turns out heights of people are normally distributed. So this is a rough graph of a rough histogram of the heights of 100 adult women. So most of the women fall in here. It's the most frequent column. And then, so that's like what we would call the average height of an adult woman. And then these would be kind of taller women, and these would be shorter women. And then if we continue to increase our sample size, we would get a shape that looks more and more like this until we get to, I'm just going to jump right down to what a normal distribution looks like. I'm going to jump all the way down here. Yeah, looks like this. Well, we'll go back here. Sorry, I'm jumping all over the place. Well, let's just do this one. It looks like this. So what happens is the center ends up being the mean, and then half of the data falls above the mean, so 50% of it, and half of the data falls below the mean, the other 50%. There's a nice formula that we're not going to talk about or look at because it's kind of crazy. You need calculus to really understand it, but it's what we used that draws this shape. We could type it into Desmos and we get a nice look at it. And it turns out that what this curve, we call this a curve, and this area under this curve is represents both, well, it's like its area and it's a percent of the data. And it can tell us how many data values fall within, say, a range of numbers. So let's read this little statement. Am I driving you all crazy? Maybe we should pause and figure out what page I'm on. This is one of the pages in your textbook. So a probability distribution that plots all of its values. Thank you. This is page 489, y'all. In a symmetrical fashion, and most of the results are situated around the probabilities mean, is called a normal distribution. And then we got values equally likely to plot either above or below the mean. So what we have is the value in the middle of the distribution is what happens most often, and it is the mean. And then we have this symmetry about the mean, meaning we got the same amount of values above the mean, the same amount of below, and it's tapering off on either end. And then the key point here is that the area under the curve is the percentage of the data values that fall between those values. So let's look at the example. Here we've got a normal curve, and we're claiming that this normal curve represents the heights of women in the United States. It should be labeled. This graph should have that labeled. All right. So the other thing that is important to note and that we don't often show here is this really, this y-axis is kind of like frequency. It's technically area, but it's also frequency. And then the x-axis here is literally the height. So remember, we said that the middle of this graph, the exact center, would have the most area, is where the mean is. So the mean of this distribution is going to be 63.7. I believe these are in inches. Does it tell us here? There it is, inches. So another way to say this, if you think back to what we did in 4.5, if there are no outliers, then the mean is the best measure of center or measure of average. So this is the average height of a US woman. Also known as the mean. Okay, so then we're asked what percent of American women are between 57.4 inches and 59.1 inches tall. So here are those values, and we're told from before that this area under the curve represents the percentage, albeit in decimal form. So we would take that decimal area, multiply it by 100, and we would get the percent, just like we did back in Unit 1. So 3.4% of all American women are going to fall between 57.4 inches and 59.1 inches tall. Another way we could talk about this is we could say the probability of selecting a woman that is between the heights of 57.4 and 59.1 inches tall is 0.034. Like if I randomly selected a woman from the population of America, there's a 3.4% chance she will be within these heights. So there's not too many people, not too many women that are this tall. Okay. I would like you to answer number 7. Let me give you like 2 minutes to try to figure that out. Let's say 3 minutes. Set a timer for 3 minutes. When you get the answer, type it in chat. Whoops. Okay, that was yes, I'm unmuted. That was 3 minutes. I got one answer in chat. Maybe my first question to you all should be, what percent of women are between 63 and 66 inches tall?
Would it be 30 and a third?
Nice. So 30, this is the percentage. Good. 30.3%. And then we're told that there's this many women in a college football game. So we just need to calculate 30.3% of that number, which is just multiply, if you recall from unit 1, and that's the amount, which I believe is what? 9,637 women. Cool. Cool. Does that make sense, y'all? So the key connection here that you need to make is that this area under the curve, this area represents the percentage of the population that has the given characteristic, whatever that characteristic may be. All right, so turns out there's this thing called the empirical rule. And I'm just going to skip to it. He tries to have us like build it out, like figure out what it is, but I'm just going to skip right to it. This is the empirical rule. And it states that if a distribution is normal, so if a data set is normally distributed, so if we created a frequency distribution and we discovered, we drew the histogram and it had a shape that looked like this, and we could say, oh, this is approximately normally distributed, then we would know that 68% of the data is within one standard deviation of the mean. Now, remember, we calculated that standard deviation Wednesday, Monday, whatever the last day it was. And that standard deviation is the average distance all of the data values are from the mean. And that standard deviation is only a good measure of spread if the data set is normally distributed. So when our data are normally distributed, this is a true statement. And this is what we call the empirical rule. This should go in your reference sheet. This is the thing you're drawing in the unit project. This is the thing you're doing on the 4-7 worksheet. You're putting this piece together. These percentages are always the same. So between the mean and the first standard deviation, it's 34%. Between that first standard deviation and the second one, it's 13.5. Between the second and third, it's 2.35, and so on and so forth. So we're going to kind of draw one of these. Well, he does it for us. Let's do the worksheet one. Let's draw it. So open up your stuff. Where is it? Go to page 51 of your worksheet. And here I'm telling you that there was this infamous 130 exam 3. You didn't have to take unit exams. You all get to do projects instead of exams. Back in the day, we used to do exams that I wrote, and it was a tough exam for students. And I had 226 students that took it, and there was a mean of a 61% with a standard deviation of 22% on that exam. So what we're going to do is fill out this normal curve. We're going to assume that we're going to assume that all of these test scores are normally distributed. And we're going to put in this mean of, let's do sample. Put in this mean of 61% and this standard deviation of 22%. We're going to fill that in here. How does it work? Well, first, you all tell me, where does the 61% go? Yeah, the exact center, right? The mean of a normal distribution, or the center of a normal distribution, is always the mean. Okay, so how do we get these upper values, these upper tick marks? What do we do? Like, what is this telling us? X bar plus S. What does that mean?
I forget what S is.
No worries. S, so let me remind you back from 4-6. So sigma is population standard deviation. That's an answer in the project, by the way. And S is sample standard deviation. So for us, the S in this problem is 22%. So this is the S. And what this means is add the standard deviation to the mean, and that's the number for the first tick mark above. So I'm going to do 22 plus 61 is 83%. That's the first tick mark above the 61. I'm going to do it again. So this is the mean, right? This is X bar. This is X bar plus 1 standard deviation. Add 22% to this, and we get 105%. That would be X bar plus 2 standard deviations, because I added 22% to 61% twice, right? Do it one more time, right? Add 22 to this, and I get 127%. That's X bar plus 3S. How are we doing? All right. What do you think you need to do to get the below tick marks?
Subtract S.
That's it. Subtract it, right? Okay, so I'm gonna let you do that. Or I'll just, whatever. It's just calculator work. Who cares? So 39. Subtract again. 17. Subtract again. -5%. Okay. Now, if you read what it says, fill in the normal curve above using the exam mean and standard deviation. Let's go ahead and put in the percentages too. And I'm just copying and pasting these. All right, these are the same every single time. This is the approximate percent, the approximate area under the curve for each. So this is 34%. This is 34%. Now, if I add these two together, which is what that little empirical rule statement said, we get 68%. What that means is 68% of the students who took the exam scored between 39% and 83%. That's the claim, right? That's what, if these are normally distributed test scores, that would be true. And then the next was 13.5% here and 13.5% here, 2.35% here, 2.35% here, and then 0.15% and 0.15%. Remember, these percentages are of the data. Down here, these are the test scores. That's what the x-axis is. Test scores. So try number 2. Figure out what percent of students scored below 39%. I'll give you like 2 minutes. Set a timer for 2 minutes. Okay, be very careful with this. So we're going from here to here, right? So we're going to do 13.5 Did I get these percentages right? I did. Plus 2.35 plus 0.15. I think you all are right. And I'm just like, yeah. Yeah, so it's exactly 16%. Good. How many are above 83? Yeah, right. So if you look, you knew that answer immediately. Remember how these are symmetric, right? This was 2 standard deviations below the mean. That was the boundary line. So this is 2 standard deviations above the mean. So this is the exact same amount of area. It's just on the other side. So you didn't have to do any work. You could just use your understanding of symmetry to note that it's the same. Excellent. Okay, so it looks like you're getting the point, right? The next one, be careful. It says how many students scored. I'll leave that for you to practice. We're going to go back to the notes here for just a second. You're going to figure out the percentage and then use the number of students in the data set to calculate the percent of. Jennifer, which percentages are you talking about? Because there's, it's not a dumb question. There's so many percentages up here on the graph that I want to make sure. Great question. Okay, so the question, y'all, is how did we get these percentages? These are, let me say it this way, theory, meaning these are always true. So when we say this data set, when we say it's approximately normal, this pops into your head. You've got that memorized, or this is on your reference sheet. So these little percentages are just the known percentages for a normal distribution every single time. Not a dumb question at all. And the thing that I've always found with this material is because there's a question on the final exam. Yeah, no worries. There's a question on the final exam that's like exactly like this. And the students that come to class and work through the problems crush it because it's not overly complicated. You just need to know this theory. And then the students who have, it's obvious who doesn't have the time to watch the videos, they have no clue what this is because most students have never seen this in your life. Like we don't tend to teach this in high school, although maybe that's changing. Okay, so we now know the empirical rule. We know what this what a normal distribution looks like and how we can use it. We're going to add one other thing to it, and that is what's called a Z-score. So I like how the author introduces this topic. You may have heard of the standardized college entrance exams. There's the ACT and the SAT. And they have a different scoring scale. Does he tell us what the scoring scale is? I don't think he does. I think you all might know better than me. I think the ACT is out of like 36 points, right? And the SAT, this is like back when I took it, is out of like 3,200 points or something like that. Like that's the scaling system on them. I don't quite know, right? So the author asks a great question. Do we think they're normally distributed? They're they're these companies try to write them to be, right? And the goal of these exams is to determine if a student will be successful in college. And colleges historically use them to decide, should we allow you to come to our school? And it's like, will you pass classes if you come to our school? Because that's what a college wants. We don't want students to come to school and then fail, because if you fail out, you don't make money and it makes the school look bad. And it's just, it's a not good. We want you to come and pass. The more classes you take, the more money goes to the college, kind of situation. The sad reality of these exams is that they are a much better indicator of how much money your family makes. Like there's a fair amount of studies that show it has a much stronger prediction measure of your zip code than it does of your academic skill. Meaning, it measures like what kind of resources you had access to, not how successful you'll be in college. The age old, if you've got money, you tend to have more, you can score better on ACT, SAT. The other thing is they're written for a particular subset of the population. At any rate, they do tend to have normal distribution of scores. So what we want to do is compare these two exams and see, like, if a student took an ACT and got their score and an SAT and got their score, like, who did better? But they have different score methods. So what we do is standardize them by creating what's called a Z-score. And it is a way of comparing two different populations that have different means and standard deviations. And what a Z-score is it's a measure of how far above or below a mean a data value is. So this sentence right here, you should put in your reference sheet. When I ask you to interpret a Z-score, this is what I'm wanting you to tell me. A Z-score tells you how many standard deviations a data value is from the mean. It's a measurement of distance in terms of standard deviations. So a large positive Z-score means you're really far above the mean, and a small negative Z-score, or like a large negative Z-score, means you're far below the mean. So we're going to fill in the blank for this. Like if you have a Z-score of 0, that means your data value is exactly equal to the mean, because there's no difference between your data value and the mean itself. And then if your Z-score, if you're one standard deviation above the mean, your Z-score would be exactly 1. So these are kind of like special little values. And we call this particular normal curve a standard normal curve. It's not, and it's used a lot in our 133 class, but you don't have to particularly worry about that. Mostly what I want you to do is know how to calculate a Z-score. So how do we do it? Well, there's a nice little formula. And I'm going to skip down to it. Where do they give it to us? Here it is. Notice these are samples values and these are population values. So recall that X bar is a sample mean and S is a sample standard deviation. Again, I'm asking you in the project to show me you know these two symbols. And then mu is a population mean. And sigma there is a population standard deviation. In terms of the calculation for X bar and mu, it's exactly the same. You wouldn't know the difference between the two. But the calculation for S and sigma, it's different. There's a slightly different formula. Check back in the 4-6 videos for how to get those in Desmos or Excel. All right, I'm going to give you a better formula for this because we don't need all this. I'm going to give you the words. The z-score is equal to whatever the data value is minus whatever the mean is. We don't particularly care whether it's a sample or a population. It doesn't matter for the calculation, divided by the standard deviation. That's it. If you're using your old school calculators, you need to make sure you have this in parentheses that the subtraction is done before the division. Otherwise, the mean will be divided by the standard deviation and you'll get insane z values. Note, these are unitless. You can think of them as standard deviations, actually, if you want. And we tend to use 2 decimal places for them. So let's do a nice little problem. Here we are. We've got an ACT had a mean of 22.2 and a standard deviation of 5.1. And then SAT had a mean of 1060 and a standard deviation of 195. So then we've got these 2 students with these 2 different scores. Each one took it a different exam. We're going to figure out who did better based on standardizing their scores, based on calculating a z-score. So what I'm going to do is I'm going to label the means and standard deviations. So I'm going to say the mean of the ACT score is 21.2, and the standard deviation of the ACT score was 5.1. That's why I have a subscript A. I need those 2 values to calculate the z-score for the student who took the ACT test. I'm going to have to do a second calculation for the SAT score. And I'm using the population symbols here because these are the means. We're to assume that these are the means for all students who took the exam that year. So we got the ACT mean of 1060 and the SAT mean of what was it? Or SAT standard deviation of 195. Okay. And then the student who took the ACT got a 26. And the student who took the SAT got a 1230. We're asked on instinct, and I don't know that that's an instinctual thing, who did better. Really, I think we're supposed to glance at these and try to logically determine who did better without doing the calculation. Part of me is like, I don't know. Maybe if we knew what the maximum was, like 26 out of 36 is what this one looks like versus 1230 out of 3200. I mean, I don't know what the maxes are, so I can't really, it's hard to guess. So let's just get the z-score. So for the ACT student, we're taking the 26, we're subtracting the 21.2, and we're dividing by the 5.1. This will get us their score. For the SAT score, man, my house smells like burnt toast. I'm gonna let you check that while I see if my house is burnt. Okay, I think I'm okay. I'm gonna do these in Desmos. That's my favorite calculator. Should be yours too, just saying. One of the nice things in Desmos is you can create the fraction if you just hit the division button, and that will help avoid some of the calculator entry errors. There's our ACT z-score. There, I forgot to put it. And there is my SAT z-score. So 0.94, 0.87. So who did better?
.94.
Yep, slightly higher. They're just a little bit better than the SAT student. So that's it. If we were to interpret these scores, we would say that the ACT person scored 0.94 standard deviations above the mean, and the SAT person scored 0.87 standard deviations above the mean. Okay, I'm going to pause here, and I want you to, where is it? I want you to calculate the Z-score on your 4-7 worksheet. So this says, what was your exam 3 score? Well, y'all didn't take exam 3 score. So let's say everyone scored let's do a 72%. Calculate the Z-score for a 72%. Right? Note, I've written down these things. What would a 72% be as a Z-score? Let me give you like 3 minutes to try that. So the timer for 3 minutes. Okay, I got one answer back. How are the rest of you doing? Need another minute, or you all got it?
So I'm thinking we subtract the mean, which is 61 from 72, but what do we divide by?
The standard deviation. Whoops, I got the wrong symbol here. So like
And
these are
that would be 72 by minus 61.
Yep. So,
Okay.
yeah, 72 minus 61 divided by 22. That's our thing. And it's exactly 0.5. What does a z-score mean in relation to the average?
Wait, so why do we divide by 22 again?
So the how we calculate the z-score is it's the data value minus the mean divided by the standard deviation. That's the calculation. So the 22 is the standard deviation. Does that make sense?
And how do we find the standard deviation that we're dividing by?
It's got to be told to you in the problem.
Okay.
Or you have to calculate it. So what sentence should we write here? Yeah, we haven't done question 5. We'll come back and answer that one in just a second. What is our, like, what do we say about this? What does this mean? This 0.5.
That's the z-score, right?
Good. So what does that z-score mean?
How far we are away from the mean.
That's it. So we're 0.5 standard easy. There we go. Standard deviations above the mean. That's what I'm asking you to say. 0.5 standard deviations above the mean. That's the answer to this question. Okay. So, well, does that make sense? Is everyone how happy is everyone about that answer? Okay, good. So let's talk about this normally distributed. So I said let's assume that these are approximately normal. What evidence is there that these are probably not approximately normal scores? So look at all the values for the standard deviations. What do you notice? For example, what's the -3 standard deviations below the mean?
So I think normally on test scores we don't have above 100% and below 0%.
Yes, 100%. Now, sometimes you can get a little bit above 100 if there's extra credit, right? Sometimes, but math classes, there's a policy. I think it's usually in the syllabus that we don't give extra credit, but definitely you can't get below 0%. That'd be crazy. I mean, that would be awful. So that's our clue that these are not normally distributed data values that I said it was, but in reality they were not. So the negative -3 standard deviation and over 100% +2 and +3 standard deviations suggest it's not normal because those values aren't possible, right? And based on the empirical rule, between -3 and +3. So between this, let me do it in red so we can really pops. Between this standard deviation and this standard deviation. So that's -3 and +3 standard deviations away from the mean. That should be 99.5% of the data. And those are impossible data values from our data set. So that's our clue that we do not have a normally distributed data set. Good. Okay, I want to pause here. We've closed out 4.7, right? So there's really two things you should know from this. You should understand the normal distribution and how it's kind of broken down by the empirical rule, and how to do calculations of percents of data. And the second thing is you should know what a z-score is, and how to calculate it and what it tells you about the data value. So you should know those two things. What I want you to do is run to Canvas and open up your project. And download the milk data. Okay, internet, come on. So what I'm talking about is this whole milk data here. So open this up. And so what we're doing here, oops, I've already talked through the Unit 4 project stuff. I've already talked through task 1 and 2 on how to do that. This is task 3, what we're doing, right? So what you're going to do is we're going to assume that this data set of milk is normally distributed, and your job is to draw the normal distribution using the empirical rule, and we're going to include the standard deviations and the percentages. So what we need to do is calculate the mean and the standard deviation of this data set. So I have two things here. I don't know why I did this, but one of them is a column of all the data values, and there's a lot of them. There's what, 130. And then over here, this is actually the source material, and they're like kind of in rows and columns. So you can see this is data from 2010 to 2020, and this is whole milk, a US city average price. So it's cities, not just everywhere. I think it might be easier to calculate the mean from the column. It doesn't matter, either place. Just a reminder how to do this. You're going to do, to calculate the mean, you're going to hit equals and type average. That's how Excel calculates the mean. Since I have it in a column, you can just select that column, and there it is. And for the standard deviation, you can treat this as a population or a sample. It's up to you. I would say this is probably a sample because it is not all of the years for which milk has been sold. But I would just make sure you acknowledge what you've done when you do your calculation. Okay, so you're going to do that. And then you're going to draw, that's stats, we don't need that. You're going to draw this. Now, I've had students do it a bunch of different ways. I've had students like do it by hand on a sheet of paper and then take a picture of that and upload it. I've had people do something like this blank normal curve template. So they Google it, and let's see, let's go to images, and like this would be a good one maybe from Khan Academy, and copy the image and then dump it into Excel. Let's see how nice it pastes. It didn't paste at all. Okay, it's up to you how you do it. It might just be easiest to just hand draw it. And you're drawing this thing. So I want to see these percentages, and everyone's going to have the same percentages. And then on this axis, you're going to have the mean of the milk and then the standard deviations going up and down. Does that make sense? That takes care of number 1 and number 2. Okay. Number 3, you're going to go find the price of a gallon of whole milk somewhere and give me a screenshot. Let's see. Does Target have it? Gallon whole milk. Apparently I bought some Legos the other day. Seems like a thing I would do. Okay, so this whole milk is going for $2.79. Wow, $7.69. Yikes. So if you haven't figured out how to do a screenshot, you can do this old insert thing. Come on now, computer, figure it out. Insert, and where is it? Screenshot, screen clipping. I guess this one doesn't like doing it. Word will do it. 286 at Meyer. There you go. Aldi's is like everyone's favorite. Go to Aldi. It doesn't matter. It doesn't matter where you get it. I just want to see that you did a real world one. So here's the screenshot, and I do screen clipping. There we go. 769. Okay. And then I'll just copy this. Will it paste into here? No, that's the other one. There you go. Okay, so you're doing that. And then I'm asking you to calculate a z-score. Using the mean and standard deviation, calculate the z-score of the price you found, right? So it's just that price of milk minus the mean divided by the standard deviation. And when you interpret it, you're going to say, oh, this is this many standard deviations above the mean or below the mean. Just a word of caution. Most likely your values are going to be large or small because these are average prices. If you look at what this is an average price, and you're selecting an exact price. Okay. So don't be alarmed if you get kind of wild numbers. You can expect that. The other thing to note is these are of cities, and I don't know that Jackson counts as a city. Or like if you go to Summit Township, or you go to or you live in Grass Lake or Hillsdale, I don't know that fits the definition of a city. It's probably cheaper. Any questions on that?
I have one.
Yeah.
So for the I'm not exactly sure what those lines are that go up and down, but so since they're like 34 and hold on one second. They're like 34 and whatever the percentages are. Do we just do the percentages of those away from the mean? So like multiply the decimal version by, you know what I'm trying to say? Is that what we do?
Let me make sure. So when you're talking about when you're filling in the graph, right?
Yeah.
So you are copying and pasting this every single time. This is the same every time. That never changes. That's the theory.
But to fill it in, do we do like the 34% times what the
What you're filling in on the x-axis is what's the mean. So let's say we find that the mean is, I don't know, 72, and the standard deviation is, let's say 70 and 5. So what your job would be is the mean goes in the middle. We add the standard deviation above, and we subtract to get it below. Does that make sense? So when you're filling out the graph, there's really very little calculation going on, and you don't use the percentages for anything. They're just there. You use the percentages when we ask you questions like how many students scored between these two x-axis values. Is that helping, or am I not understanding the question?
No, I think I'm not understanding like exactly how we're supposed to fill the graph out because if we already calculated the mean, right, with Excel.
Okay, good. I'm with you.
So I think I'm not understanding how we're supposed to fill out the graph.
So where would the mean go in the graph?
Dead center.
Nailed it. Okay. How do we get the first line above the mean?
Oh, we subtract the mean from whatever it is that we've got, and then the divide by something.
You're mixing up the z-score and um, putting together the graph. So what you're describing is calculating a z-score. When we do this graph, you literally just add the standard deviation to do the above and subtract to do the below, and that's it. So if I'm going to do the first tick mark above, I'm going to add 0.24 to this 3.23, and I'd get 3.47. That's the first one above. And then how do we get the next one?
I'm not sure.
Add again.
Okay. And
how do we get the next one?
How did we get the 0.24 again?
Oh, we calculated it. So I just said, well, what's the standard deviation? From 4.6 to calculate standard deviation, the function is stdev, and we did a sample standard deviation because I treated this as a sample. You could treat it as a population if you wanted to. Here, let me get the wrong answer. There's a different answer.
Okay. I think I got it now.
So, but let me double check. How do you get the numbers below? What about this direction?
Aren't they just negative what you've got?
That's it. So I would subtract whatever the standard deviation is, and I need to do it 3 times. And your little, I don't know, cheat sheet isn't the right word. Your format to remind you of that is this thing. Where is it? Right here. Oh, no. This one right here. Here it's saying, take the mean and add 1 standard deviation to it. Then add another standard deviation. So I'm just adding 1 standard deviation to this one, and then add 1 to that one. And here, subtract it. And then subtract another one, and then subtract another one. And that's, you've built your graph. Okay. Why does this keep flashing? Close. Other questions? Those are good questions. Let's do the lesson check before I forget, because you know I'm going to forget. It's my standard operation. And then we should all do like 10 push-ups. Hey, don't get this wrong because you're only allowed one attempt. Answer question 7, page 490. How many of them would you expect between 63.7 and 66 inches? We already answered that. That was this one. 9637. We would expect 9637. Doop. Yep. Okay. Let's do the last section. And to me, this last section is like the most important section of all. It's the most fun. Okay, so the last one, 4.9, we're talking about, I like his title, Trust No One, or believe that everyone is trying to mislead you for particular reasons. And so there's several books out there, like there's one called How to Lie with Math or something, or there's another book by mathematicians that talk about how people tend to believe you when you attach numbers to things. Um, it started out with do you remember? I don't know. I wasn't alive when this happened, or maybe I was, but like the Red Scare, where there was this um, representative from Wisconsin that walked into the House of Representatives and was like, "There are 120 communists in this room today," and like he had this list of other Congress people who were secretly members of the Communist Party. This was like during the Cold War, and of course that was a terrible thing. And his goal was to root them out. And it turned out that no one was actually affiliated with the Communist Party. But the fact that he had this number, like, set off this witch hunt and made people believe things. More recently, the questioning of the election was the authenticity of election results were based off of numbers and like a not understanding of how numbers work, I think, and other things. And mathematically everything was sound, but that's neither here nor there. So the goal of this lesson is to look at how sometimes people misuse sampling to try to get to answers that aren't real, to like mislead. And others are, the biggest one I want to get to is how graphs are manipulated to tell particular stories. So misleading graphs. So the first thing, remember the 4 sampling methods we talked about. There was just a simple random sample, just randomly selecting things and making sure we carefully how random is done, that there's some sort of random process. And then there was the systematic and the stratified and the cluster sampling as ways to ensure that there's not bias when we build our sample. Which reminds me to remind you that when you do your project, I talked about in the 4.4 video, I showed you how to use Excel to generate a random sample. I think I showed you the 2 main methods how to do this. Most students lose points on the project when they don't describe how they did their sampling process. So make sure you write a little paragraph, a couple sentences describing the method you're using. And you can use the definitions that I wrote in the notes on the video or the definitions from the textbook to help talk about if you just did random and you give a little description of it. Right? That's important to me that you're clarifying what you're doing, because that shows me you understand what's going on. So one of the big things that news folk will do when they're reporting things is they don't talk about the sample size. So our author points out a couple things. There's 300 million people in the US, about 7 billion in the world. And then a lot of statistical studies involve sampling, like all of them do. And so there was this chewing gum brand. They had this large campaign that said 4 out of 5 dentists surveyed would recommend their product. Right? First, we should start with what's that as a percent? And I think we all know that's 80%, right? Maybe you even remember the old school way to do this. Whoops. 5 goes into 0, 5 goes into 48 times. So this is 0.8 or 80%. So 80% of dentists would recommend you chew this gum. That's like a really good recommendation. Well, then the author's like, well, how many dentists are there in the US? I don't know. 50? No. I think about Jackson. There's probably 50 dentists just in Jackson. How many dentists do you feel like you'd have to survey to make this statistic meaningful? All of them, maybe. You would need a random representation of all the dentists. And also, you would need to make sure they were not dentists that were being paid to for their endorsement. So this is a very anytime you hear this kind of claim, it's a very suspicious claim. And it's probably like they probably actually did the survey. And then there's probably a little asterisk and some really fine print down at the bottom that describes it. My favorite one is the commercials where you're told to ask your doctor for a particular diet drug, and then it talks about what the sampling was of the people who took the diet drug to lose weight. And usually it's like the people in the sample ate a strict diet and exercised 5 times a day. And it's like not your typical person that took the diet drug and then lost weight. I think our author's making a big point here. Why would they leave it out, the sample size? And that's because one of the things to recognize is that to really do random sampling to eliminate bias and to get a good sample, it's costly. We'll even write this. Good samples are very expensive. It takes time and money to generate them. And so mostly these types of things are ridiculous statements that you should just ignore. All right. The second one, we already talked about this, volunteer participation. That means it's a convenient sample. Anytime we have convenient sampling, it's garbage. The convenient sampling means that the people who respond are only people that have strong feelings. So convenient sampling generates information about a particular set of people, but not about a population. That's what we're stating here. Have you ever seen a movie Fun with Dick and Jane? It's not Will Ferrell. What's that guy's name? Jim Carrey, and I forget the woman's name. And they rob banks, and he was wealthy, but he was in a part of the company that crashed, and they're trying to make money. And the wife does a study where they're paid, and she has a negative effect. That's an example of volunteers being paid, and you get a bias. So maybe you get a particular socioeconomic subset people that need the money will go participate in the study more so than just a random set of people. That means you can't generalize it to a larger population. Let's we've already talked about giving an example. I want to get to the good stuff. Okay, so what is this? We've talked about averages. Do you all remember the 4 types of average from 4, 5? What are the 4 types? Nice. There's one more that's even super garbage. Those are the main ones: mean, median, mode, and then the last one that you're calculating in your project is the mid-range. So all 4 of those are correct measures of average. Yeah, something else. Nice. And they're all measures of, remember, the center or typical value. But remember, the best measure of average is typically one of these 2, and it depends on, are there outliers or not? So the mean is good, really, from what we just learned, if the data set is normally distributed. And the median is best if there are outliers present. So when we talk about income, median is always the best measure of average, because median kind of ignores the size of the data values and looks at the position of the data values. The author points that out here when he's talking about the mean years of service for these 4 salesmen of 9 years versus the median, which would be 6 years, be the median here. So that's a better measure of the center. And news organizations will report the mean when they're trying to mislead you, when they're trying to push your thoughts in a particular direction. Another way you can be misled is how questions are asked. So bad survey questions. So check out this one about gun control, a hot button topic. Do you favor a waiting period before guns are sold? Do you favor a national gun registration program costing about 20% of all dollars spent on crime control? Note that this extra information here includes a particular bent of bias that pushes a reader or respondent to think a certain way. If we wanted to know what the reader actually thought, we would take out this cost and we would just ask them this: do you favor a national gun registration program? You can see that how people responded was totally different between the 2. And depending upon who was offering the survey would say, hey, look, America doesn't want stricter gun control, although these are also 2 different types of gun control. So generalizing this as to how the population feels about gun control, I think, is unfair as well, which is what the author has done here. This is a very specific type of gun restriction. So these are all different types of bias that could be introduced in how we ask questions. So the questions themselves could have biased, or you have 2 ideas in one question, or double negatives, or you have confusing words. This, by the way, was the claim here in Michigan for Proposition, what was it, 3, I think. I saw that sign in a lot of yards as I drove around Jackson. It was just the big word confusing. I was a little confused about what the folks were confused about, because it just stating the word confusing to me wasn't particularly helpful, but that was certainly a claim. All right, so I'm going to skip down a bit to the misleading graphs. All right. So one of the things about graphs is it's a visual representation of numerical values. So here we've got two graphs, and they have different scales. And what we're going to do is draw the information back from question 24. So in 24, we're told that in North Carolina, the individual income tax rate was 7.75, and then it was 5.75 in 2015. So it was first 7.75 here, and then it was 5.75. So we'll just do a quick calculation here about the difference between these two numbers, and we'll get the actual difference. So there was a 2% drop, right? That's the fact. That's the numerical value. Now I'm going to draw a bar graph of these two values. 7.75 would go here-ish, and 5.75 would go here-ish. Okay, so there's our visual difference between the two. The second graph, if we draw it using this scale, note the visual difference. So in the first graph, it's just this amount, right? That's the visual amount. It's not particularly large, and really I probably didn't draw it as good as I should have. This should be up even a little bit higher. It should be a little closer to the 6. Whereas in the second one, it almost looks like this bar is like half as large as the other bar. I mean, you can count the number of bars between the two. Oh, and I've even got, geez, I even drew this one wrong, right? 7.75 should really be like up here. So the way the scale is drawn, which by the way, both of these are drawn correctly in terms of the scale. It's just this scale highlights the difference between the two. It's like zoomed way in, like we just took this and zoomed right in to exaggerate the difference between the two bars. So to the unsavvy reader, you would just look at the visual difference between the 2013 and the 2015 tax rates and think, wow, whoever voted here cut the taxes in half, because this bar is about half as high as this bar, although I'm still not very good at my drawing, right? Because it should really be up to here-ish. Someone who leaves off the 0 in their scale is attempting to mislead you visually. They're attempting to make a difference between two numbers appear larger than it really is. Now, if you look at the actual numbers and you're just like, oh, well, it's a 2% difference between the two, you are not misled. You know the difference, but I don't know. It's just a common thing that happens. Is that making sense, y'all? What's going on here? All right. I've got one I'm going to email to you all for you to try out. Oh, wrong class. Same wrong class. Jeez, what? Look at all these classes in here. Which one is it? Oh, we're I3. There we go. That's one of these sections. Yeah. So this is the 4-9 worksheet. So I gotta find where I put it. Okay, here we go. So what? So sorry you have to do this digitally, but it is what it is. Okay, here we go. So let's start with question 3. Let me give you a second to find it and get it open. And then I've got these little graphs compared. Let me know when you got it and are ready to go. I sent it through Canvas, so whatever that, however you get your Canvas emails. So I don't know if you have your Canvas emails sent to your personal email or your school email. We'll be right back. Where you get that? Okay, y'all, which graph is misleading? Left or right? Why is the left graph misleading? Yeah, so visually, it's making the difference between the interest rates look large, right? It's not necessarily a wrong graph, right? That nothing about the graph is wrong in terms of how it's constructed. It's just visually misleading because it makes it look like in 2018 the interest rate is like, or like the 2012 interest rate is growing exponentially if we connect that back to what we did in unit 2. This might be someone trying to claim that I don't know, like the economy is bad because interest rates are going up, or maybe it's positive. Maybe monetary policy is good because interest rates are going up. Someone might be trying to make a claim here that this increase is good or bad. When in reality, like there's almost no change, and you can see that, right? Because 3.152 minus 3.140 is a difference of 0.012%. Like that's the amount of difference between the 2018 value and the 2012 value. But if you don't pause to do that calculation, and just look at the picture, you could be misled. All right. And then I've got another question up here. Consider the following 2 survey questions. What kind of like bias is contributing to them? So I want you to circle the words or phrases that contribute to bias in the question, and then state how it does contribute to bias, and then rewrite this answer, rewrite question B to eliminate the bias. I'll let you do that. I'm curious what your answers are. I want to show you the last piece of the project. And then I will say, hasn't it been wonderful? See you on Monday when we work through the Unit 4 reviews and prep for the final exam. So task 4 of the project is pick a graph from the misleading file worksheet, explain what the graph is saying, explain why it is misleading, and explain how you could correct the graph. So I've uploaded some selected misleading graphs right here. So let me open that, and you pick any one of the, oh, come on. You pick any one of these you want. What you would want to do is download it. It's a PDF. And yikes, that's hard to view. There you go. I guess you could zoom in. So you need to tell me, like, if this is the graph you pick, you need to tell me what this is talking about and how it might be misleading. There's that graph. There's this graph. There's this graph. This one, or this one, or this one. Okay. Any one of these graphs you can pick. I'm just going to mention, I know there are 2 from Fox News. I have nothing against Fox News. It just so happens that they are one of them. They produce a lot of really bad graphs, unfortunately. They're well known for doing it. And if you Google like misleading graphs, they have a lot. They are not the only ones. The other news organizations do the same. So it's not just them, but they happen to have lots of them. So you pick any one of these, and what you would do maybe is open a Word document if you wanted to. New Word document. And you can just, if this is the graph you wanted to do, screenshot it so I know which graph you picked. So do your insert, screen clipping, and do your thing from there. Or if you want, you can just take the PDF and write in the PDF, like you can add text and type your stuff in there under whichever graph you pick. And you only need to do one, but you do need to answer those 4 questions. All right, any questions on that? Lesson check 4.9, let's do it. Last one ever. Oh, doesn't that sound wonderful? Okay, we totally skipped this question. Which one is it? Question 13. Nope, I answered it. 6. So I guess I could share my screen, couldn't I? Mike, I don't know what you're asking. What's for the project?
The thing you were just doing with the graphs and stuff.
Yes, that misleading graph stuff. Yep.
And where do we download that again?
In Canvas, under the modules for projects, there's a misleading graph thing. Real quick while we're here,
Okay.
question, the answer to the lesson check is 6 from page 527, and then here, Mike, I'll show you where that's coming from. The misleading graphs PDF. I should just put this project 2 data up here. There. Lesson check 4.9. Median of 6. Okay, that's it. Like I said, on Monday, we will go through the unit 4 reviews A and B. And I will also talk about the final exam, although I've already talked about the reference sheet material for that, for the unit 1 review, the unit 2 review, the unit 3 review, and then I will add the unit 4 review reference sheet material. It'll be the same thing. And I can highlight that on the YouTube videos. I guess I could do that right now if we wanted to. If you go to the recorded sessions, since I finally started labeling them like halfway through, looks like I didn't label these. So here's the unit 1 review A work through. I would have reference sheet suggestions on that one. And then unit 2 review, I would have reference sheet suggestions on that one. Unit 3 review, unit 3 review B. This one I think is the reference sheet material here. And then here I work through the review B, all of that. And then we'll be adding in on Monday the unit 4 reviews. We'll probably do both of them, although we may not have time to get all of them done. We'll see. And then also a reference sheet write-up. And then your final exam, you would want the reference sheets from unit 1s, 2, 3, and 4, all of that together for when you take the final exam. So, any questions on anything? If you're good, then take off. Have a great weekend. Happy studies. Monday, I have my office hours 8:30, or my tutoring hours 8:30 11. I have tutoring hours tomorrow 8:30 to 11, Tuesday 8:30 11, Wednesday 8:30 11, Thursday 8:30 11, and then that would be the end, because that's the end of the semester essentially. And we won't be having class on Wednesday, but I'll probably be on the tutoring hours link, just because I'll be like there available for people to take the exam. Well, I don't know. People could email me questions to meet, I guess. I think I will. I think I'm gonna have. We'll see how it goes, because I think I have my stat students will be taking the exams, and they tend to take a long time, and I'm Zoom proctoring it, so I will probably be on Zoom, and you all can just pop in there if you want to ask questions. So, yeah, that's that.